Okay, the pulley problem. So this is, I'm going to say this is the most challenging problem on the final exam, the one that's modified from this. And so, yeah, someone in class, we won't name names, modified this to contain another pulley and some party balloons for the end of the semester. So let's go back, and what I will do is I will solve something similar to the original problem in the book. I'm not going to do exactly what's in the book because I don't want to get in trouble with publishers or anything. So I'm just going to change this force over here from 200 to 100. We'll solve this out of the book, and then hopefully that'll get you started for how to solve the modified problem, which is a little bit more complicated. And know that for all of these, if you don't get it right on the quiz, just show me your work and I'll give you partial credit. So the point of it is to know how to think through this stuff, and it takes a few attempts at all these problems before you get them right. So long as you understand work energy principles, and then I'll also throw in some force balance into this too. So it actually is a really good problem for a final exam because it incorporates so many different concepts from the semester through it. But I'm not going to be really brutal with you on the grading. So just write down your work, draw diagrams, and that'll get you most of the credit on this to show that you know how to do energy balance problems. Okay, so chapter 17. 17 really was an energy balance problem. And for that one, I'm going to open up Mathematica here. And just think of this as a calculator. So I don't want you to be programming stuff, but rather than like show a video of me typing numbers on a calculator, that's all you should consider Mathematica as. Okay, chapter 17 review. So this is all coming from our good old F equals ma again. For problems where you have displacements happening, so A is traveling 1 meter, B is, we'll figure out how far B is gone, C is rotating. There's nothing with time here, so that's why it's going to translate over to this work and energy balance equation. And it really does come back to this initial simple relationship. So try not to complicate it in your mind more than force through a distance. So what kind of forces are changing my velocity? That's the question you should ask yourself over and over again with these guys. The new thing for chapter 17 is instead of just translational forces, we're also looking at rotational energies. So instead of ds equals already theta, so this turns into moment through an angle, as well as force through a distance. And remember, this is a dot product, so you're only concerned with the part of the force that is in the same direction as your motion, the same direction as your velocity. So anything that is not changing velocity, ignore it, but draw free by a diagram and keep track of any force that is changing your velocities. For your energies, okay, so this is, we're looking at all the 1/2 mv squares. For an object that has both translational motion and rotational motion, you're going to define that velocity as a combination of translational and rotational motion. So if I take the corner of some object, right, and I want to know the total velocity of the corner of that object, if the whole thing is moving, it's going to be a combination of what the center of mass is doing, so the whole thing moving with the center of mass, and also rotation around the center of mass. And you can always get the total velocity of everything by adding those two components, translational and rotational motion together. The rotational motion part of this, so r squared omega squared, this is going to turn into your inertia, mr squared. That's the generic form for inertia, right? So we have 1/2 mv squared, that's what the center of mass is doing, and then we have rotational motion. For this guy, what that's going to translate to is B is moving, so B has 1/2 mv squared. A is moving, 1/2 mv squared. C, the center of C is not moving, so the only thing C is doing is a 1/2 I omega squared. So when we look at our ending energy of this thing, we're going to be adding together A and B, and then for C, it's going to be the inertia piece of it. And that should be just 1/2 I omega squared. Yeah, your inertia, it acts very similarly to mass. So just like mass resists translational motion, inertia resists rotational motion. Okay, starting energy. So let's walk through this huge energy balance equation, right? So you have some starting motion, and then whether you call it work or change in potential energy, there's some sort of a force through a distance or moment through an angle that is going to change that energy. And then at some time in the future, you have some new energy. So let's just go back to the problem statement. And this says, knowing that the system is at rest in the position shown. So that makes starting energy easy. We're going to start with a great big 0, right? So our starting energy is 0. And the ending point we're worried about, let's see, the velocity of the cylinder as it strikes the ground. So our ending point is A is moving down. It's got this great big force pushing down on it. B is moving up. So we want to grab the energy going on right as it strikes the ground. And so that means the position that we've moved through. So we're going to have forces acting through distances. So A is going to be going through 1 meter. B, how far is B going to move? And we can walk through how to figure out A goes this far, B goes that far. And then we'll also figure out the rotational energy, 1/2 I omega squared for this. So for the pulley, we're given radius of gyration, and that means we can calculate our moment of inertia. So inertia is just, instead of mr squared, it's mass times that radius of gyration squared. So that's what that thing is. Keep everything in meters. Check your units for this thing. So we'll use like 9.81. Okay, so we have our starting energy. If we define our system as this entire thing, so we're going to put our system boundary around the entire thing and just add up everything that's moving. So let's start out by looking at this piece of it, this A block that's moving down, and figure out FDS and MD theta. So for this one, there's no moment attached to it. It's just a force through a distance. And since A is going down, it's going to be speeding it up. So our work for A is going to be equal to mass of A times, let me put the mass of A times G. And then we also have that added force P. Okay, so that's all of our forces acting on A, and they're going to be pushing on it for a total of 1 meter. And we're going to make that positive because these two guys are making the motion go faster. So there's our first piece of it. The next piece, B. So as A is moving, B is moving too. And we need to say what forces are acting on B. Now, if we say that our system is the entire thing, so the tension is pulling down on the cylinder, it's pulling up on B, you get equal and opposite forces, and I won't have to worry about the tension yet. And I know the tension is part of it. We'll do a force balance to get that, but for now, let's just do the simplest case where we're going to just add everything together and not add the tensions. There's enough to worry about already. So I'm not going to worry about the tension in here because that's internal to the system. And I'm just going to worry about my external forces. So I have my weight acting down. Part of that weight is in the direction it's moving, right? So B is going to be moving up. And the chunk of the weight is resisting motion, so this will be negative work. It's slowing it down. I can look at my normal force, and that will let me figure out my friction force, right? So I have some friction force, and then this is going to translate into my normal force, and then this will be, so sine versus cosine. This is the sine part of it. This is the cosine part of it. Sorry, I'm trying to draw with my mouse here. Okay, So for B is slowing it down, and all those forces are going to be mg sine theta, right? So that's the chunk of the weight. And I also have that kinetic friction coefficient, it's sliding, so this will be kinetic. And then the normal force here, if you look at that free body diagram, the normal force is the cosine theta chunk of the weight. So those forces, I'm putting this in parentheses, both of these forces are slowing it down. So I have a negative sign in front of here. And what is the distance that those forces act over? And you can think of circumference equals 2 pi r, or any kind of arc length is equal to r times theta, right? So if I say 1 meter is equal to 0.25 times however far c rotates, right? So here's how much c has rotated. And if you say 1 meter divided by 0.25 meters, so that is 4 is in radians. So that is the number of radians c has rotated by the time A falls that meter stick all the way to the ground. Okay, so if we know how many times c has rotated, that translates to B. So 0.15 times how much c is rotated. So that's our distance that this force is acting over, right? So that's our force through a distance for B. So now we're through starting energy is 0, and then the work and potential energy, that mgh and mg sine theta, that's, you can think of that in terms of potential energy, or you can think of it in terms of work. Either way, it's fine. And now the last piece of our equation we have to chunk through is the final velocities. Okay, so I'll say a big equal sign and start a new line here. So our final velocities, 1/2 mv squared. What all is moving? So I have A is moving, and we have the velocity of A. B is moving, and I've got the velocity of B. And I have C is rotating. So that's going to be how fast it's rotating. Now, rather than having 3 different unknowns, velocity of A, velocity of B, and omega, let's relate those through kinematics to one another, so we end up with only one unknown in this equation. Okay, so just like we related distances, we can also relate velocities. So we know the velocity of A is equal to that radius at A times omega, right? So let's do a couple of substitutions in here. So we're looking at radius of A times omega. And here we have the radius of B times omega. That's going to be the velocity of B. So what this does is now I know everything in this equation except for the angular velocity of this gear. And if I chug through this thing, I can then solve for it. Okay, so I've gone ahead and chunked all of this stuff in here. So we've got, like, the mass of A is 5 kilograms and B is 15, and the force we decided to do with 100. There's our angle is 30 degrees over here. Our kinetic friction coefficient. Here's where we calculate the inertia for our pulley system. So we have m times the radius of gyration squared, using meters, make sure everything's in meters. We can look at velocity of A is r omega, velocity of B is r omega, and here's that ginormous energy balance problem. So we have force through a distance for A, force through a distance for B, and then the final energies for everything. So we have the final kinetic energy for A, the final kinetic energy for B, and the gears are rotating. So 3 pieces to that final energy. This is just, I'm solving, because it's squared, you get positive and negative solution, so this just gives me the positive solution coming out of here. Okay, so then I make sure that I have my radians per second for my angular velocity. And once I know my angular velocity, here's VA is R omega. And here's my VB is R omega. And I can see how far B has gone through that first thing too. Okay, so solving this guy gives us, so here's our radians per second. And again, R omega, there's how fast A hits the ground. Okay, one other thing on this. So this problem actually says the total distance that block B moves before coming to rest. When A hits the ground, B is still moving. So there's two pieces of the problem here. We have, okay, so A moves 1 meter, hits the ground, and during this time, B moves 0.15 times 4. Okay, so this is where B is at when A hits the ground. So as soon as A hits the ground, there's no more force, but it has a little bit of momentum, right? So this thing is still turning. So B is going to continue to slide up the hill because it has that initial velocity, and until B finally comes to rest at some new location right here. So if we go from state 1 to 2, and then 2 to 3, and from 2 to 3, what we're going to do is look at what velocity B has here. So we'll have some starting kinetic energy, and then at the very end, that energy is going to go to 0. So we're going to come back to our ginormous energy balance problem and look at what B is doing when A hits the ground. So that's the starting velocity. It has the forces acting on it, so friction and gravity are slowing it down until it comes to rest, until it's 0. So for that last little bit of the problem, we've got one more energy balance to do. So here's the starting velocity of B, and again, this is what's happening when A hits the ground. And we have C is rotating, A is no longer moving, so I'm still keeping the entire system together so I don't have to worry about that tension, because that's one more unknown to try and mess with, and I'll show you how to get this tension here in a second. So from 2 to 3, we have B is moving, C is moving, A is out of the picture, A is stopped, and the forces that are slowing it down are again kind of a gravitational MGH sort of a thing going on, and then we also have the friction force, and these are both slowing it down, so be very careful with your signs here. And the final energy is, we're going to say it comes to rest, right? So B is stopped moving, C is stopped pulling it, it's come to rest. And if you solve the second energy balance problem, you can get the distance that is traveled during that second leg of the trip, and then you add together both legs to get the total distance B travels before it comes to a stop. So that is this final output here. Okay, so we have that initial distance, 0.15 times 4, which ends up being 0.6. And then the velocity, this is the outputs over here. So this is the initial distance traveled, and then the second chunk of the distance traveled, so the total distance traveled by B. You would add those two together. Okay, what if we want to have the tensions in here, and what if we want to solve this a different method and check our answers? So we got things like the velocity of A. Is there a different way that we could get the velocity of A? And there is. So know that anything you learn in dynamics can be applied to anything. So you can use force balance, impulse momentum, R cross MV, any method you want, and you should get the same answer. And that's really nice. So if you have a problem and you can't check the solution manual to see if you got it right or not, you have to find some other way to see, oh, did I get everything plugged in right? Just use a different method to solve it, and if you get the same answer with two different methods, then you can be sure that, oh, hey, yeah, I probably did this right. Okay, so if we go back and use our force balance method, how would we do that in this case? So this is where you draw a free body diagram, and we add the forces together, you can use, is this a constant acceleration problem? If it's a constant force, it's a constant acceleration. So it doesn't have to just be gravity to be a constant acceleration problem. So let's go ahead and solve this same thing using a force balance. So this next chunk, what I'm going to do is, let me get some figures going here. Okay, so let's do a force balance on just B, and then we can do a force balance on A. For C, what we'll do is a moment balance, because it's not moving, so we'll add together R cross F for everything going on with C, and then we can use that constant acceleration to see what the final velocity is, and see if that final velocity agrees with what we got with our energy balance method. Okay, so here we go. Forces acting on B. So what do we have here? And in this case, I am splitting it apart. And so we are going to include the tension on this. So let's call this just the tension on B. We have the weight acting on B. And let's go ahead and split everything up into normal and tangent directions, because it'll be easier to solve. So kinetic diagrams versus free body diagrams, all of these forces, friction is opposing motion. So all of this stuff is going to add together to the acceleration, okay? So we've got our free body diagram. Okay, so here's our free body diagram, and then this is going to add together, not to zero, it's not statics anymore, right? But this is going to add together to how the thing is moving. And the motion, you always attach that at the center of gravity. And in this case, it's not moving normal to the plane, it's just moving in this direction. We don't have to worry about I alpha. It's not rotating, so we can make one equation for block B that looks at the forces adding together to the motion. So we're especially interested in these pieces of the force that are in the same direction of the motion. So again, it's not equal and opposite. It adds to acceleration. Acceleration is what happens when the forces don't balance. We can do the same thing for block A. So if we make one diagram showing the forces acting on it and another showing kinetic diagram, so we've got, and we'll call this tension A, and it's a different rope, so it's going to have a different tension. We have the force pushing down on it, we have mg, so there's all of our motions. For this one, decide which direction you're going to call positive and which direction you're going to call negative. And since it's moving in this direction, I'm actually going to write my equations up with down as positive. Okay, so there's my kinetic diagram. Forces don't add to zero, they add to MA. And then for the pulley system, so for this one, I'm ignoring the blocks. It's just going to be a matter of these tensions coming off of here. So this first tension, this is what's going off to block B. And then this other tension, this is what's going off to block A. And we're going to just look at the R cross F for this thing. So we'll add the moments together. The moments don't add to get to zero. Do you remember what they add together to? It's I alpha. So that's where you say R cross M R alpha. Remember that thing? So you end up with two R's, R squared, M alpha, and your moments turn into inertia times alpha. So force equals ma, moment equals I alpha. And so the kinetic diagram for this guy, and we know which one is winning. If you don't know which way it's going to travel, just draw it in the positive direction and those signs will work their way out. But we know that A is falling, and so it actually is going in the positive counterclockwise direction. So we have the moments don't add to 0, they add to I alpha. Okay, so if we do those force balance equations, we can solve for acceleration, and then once we have accelerations, we can do constant acceleration equations and solve for our velocity and see if we get the same velocity as the energy balance. Sorry, this is turning into such a long video. Geez, this is an involved problem. If you can get through this, you can get through anything. Okay, so force balances. Here is block B. So we've got tension acting up, weight and friction going down, and there's the acceleration of B. So here's our free body diagram to kinetic diagram for block B. Next equation for block A. So here's free body diagram, kinetic diagram for A. So we have the weight acting down, tension acting up, and we have A moving around. Next one, here is rotational motion for C. So we have R cross F. The TA is at a radius of 0.25. TB is at a radius of 0.15. These guys are trying to go opposite direction. So A is going counterclockwise, which is positive. B is trying to turn clockwise, which is negative. And those are going to add together not to 0, but to what the pulley is doing. So the moment of inertia of the pulley and angular acceleration of the pulley. Okay, once we have all of our accelerations figured out, then we can plug into our constant acceleration equations. So we don't need to worry about time. Let's use this v squared equation. We don't have an initial velocity for this one. We're just looking for the velocity right as A hits the ground here. So we'll say 0, 2ax. So here we go. We're traveling 1 meter. And there's our velocity. So out of these 4 equations, 3 force balances, force balance on B, force balance on A, moment balance on the pulleys, and constant acceleration equation, we can pull out of that our tensions, tension A, tension B, our angular acceleration, and so you can relate the accelerations to one another, right? A equals R alpha, and you can get the velocity out of this thing too. And lo and behold, 3.29, the velocity we get out of the force balances matches the velocity we got out of our energy balance. So we can be sure that the answer is actually correct because you get the same numbers no matter how you solve for it. Oh my goodness. So that was, give you bonus points if you make it all the way through this problem. And really just show your work on this thing and I'll give you most of the points. If you don't get every single number plugged into your calculator exactly right, but the point is a ginormous energy balance equation and then your force balance equations, and you can get everything. So if you add another pulley onto this, and the force on this guy is balloons, so we'll say that the weight of the balloons is negligible and all they're doing is pulling up. So any kind of 1/2 mv squared, they don't have an m. So don't worry about their 1/2 mv squared. The only thing they would contribute to is a moment. So anything you put an R cross F into, they have an F. And that would be the piece. So like a work force through a distance, you can figure out their force and what distance does that force act over. And that's going to be related to their radius, 3 meters. So yeah, this is this is definitely the hardest problem on that, and you can go have a party after you get through this one, and hopefully the rest of it won't be quite as involved as in this. Let me know if any of the other ones are in need of a video too.